Charlotte Motor Speedway, 1967. The green flag drops, 43 engines scream, and somewhere in that pack of thundering metal, one car is running a secret that will rewrite the rulebook of an entire sport. Not once, not twice, 17 times. And the man behind it? He never broke a single rule. Not technically, anyway. Welcome to one of the most fascinating rabbit holes in motorsport history. Because today we're not just talking about a clever mechanic with a long fuel line. We're talking about a man who fundamentally changed how humans think about competition, rules, and the space between what's written and what's meant. And trust me, by the end of this, you're going to look at rulebooks differently forever. This is Motorsport Heritage, and I spend way too much time thinking about the rule benders, the loophole hunters, and the mechanical geniuses who built racing into what it is today. If you're someone who loves the engineering battles, the psychological warfare, and the untold stories hiding behind the race results, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, before we get into the actual engineering, and we are going absolutely deep on this, I want to set the scene properly. Because without context, Smokey Yunick just sounds like a guy who cheated with a fuel line. And that framing completely misses what made him extraordinary. Here's the thing. NASCAR in the 1960s was a beautifully chaotic environment. The rulebook was thin. The enforcement was inconsistent. And the culture was built around a simple, almost romantic idea that the cleverest man in the garage should win. Not just the richest team, not just the fastest engine, the smartest guy. The one who outthought everybody else while they slept. Smokey Yunick, born Smokey Yunick, well actually born Henry Yunick in 1923, was that guy? He'd spent World War II keeping B-17 flying fortresses airborne over Germany. Let that sink in for a second because it matters enormously to understanding his mindset. When you're a mechanic responsible for keeping 10 men alive in a machine flying through flak and enemy fighters, you don't think about machines the way a normal person does. You think about every system, every redundancy, every interaction between components. You think about failure modes. You think about what happens when the obvious solution isn't available. You develop a mechanical intuition that most people simply never acquire, because most people never need it that badly. After the war, Smokey opened what he called the best damn garage in town, in Daytona Beach, Florida. By 1955, he was building NASCAR stock cars, and almost immediately he started doing something nobody else was doing. He wasn't just reading the rulebook to understand what was prohibited. He was reading it to understand what wasn't prohibited. And in that gap, that gorgeous, enormous gap between what was written and what was intended, Smokey found his competitive edge. Now you might be thinking, okay, plenty of people look for loopholes. What made Smokey special? And this is actually the key question, because the answer reveals something genuinely profound about creativity, engineering, and human psychology. Most people who look for loopholes are looking for one trick, one shortcut, one thing they can get away with until they get caught. Smokey was different, and here's how. He didn't think of the rulebook as an obstacle. He thought of it as a design specification, and there is an enormous cognitive difference between those two things. An obstacle is something you navigate around. A design specification is something you optimize within. One mindset is fundamentally reactive. The other is fundamentally creative. This distinction produced innovations that weren't just clever in isolation. They were systematically clever in ways that compounded on each other, which is exactly how you end up with a car that carries nearly 25 gallons of fuel while passing every single inspection with a rulebook that says 22 gallons maximum. Let's break down exactly how he did it. The fuel system saga, as it became known, started with what sounds almost embarrassingly simple in retrospect. The 1960s NASCAR rules specified a maximum fuel tank capacity of 22 gallons. They specified that the car must have a fuel line running from the tank to the engine. And then, crucially, they stopped. Diameter of that line? Not specified. Length of that line? Not specified. Material? Not specified. Routing? Not specified. Standard practice at the time was a fuel line roughly 3/8 of an inch in internal diameter, running maybe 6 feet from the tank to the carburetor. Logical. Efficient. Totally normal. Smokey looked at that unspecified space and built an 11-foot fuel line from 2-inch diameter steel tubing. And then he routed it through the entire car. Up through the frame rails, across the firewall, around the roll cage, back through the floor. Loop after coiled loop of 2-inch tubing integrated into the car's structure so thoroughly that it looked, to the uninitiated eye, like part of the chassis itself. Here's the math on why this mattered. A 2-inch diameter tube has a cross-sectional area of just over 3 square inches. Over 11 feet, which is 132 inches, you get roughly 404 cubic inches of volume. 1 gallon equals 231 cubic inches. So Smokey's fuel line, that single gloriously oversized fuel line, held 1.74 gallons of fuel. Nearly 2 extra gallons, invisible to any inspector who measured only the tank itself. The execution was equally brilliant. During inspection, the car arrived with a bone-dry 22-gallon tank. Inspectors measured it, confirmed it, moved on. The fuel line, sitting there integrated into the structure, full of fuel, was never questioned because the rulebook said nothing about measuring fuel lines for capacity. After inspection, the crew filled the tank with exactly 22 gallons of race fuel. The car lined up carrying almost 24 gallons total. At 4 miles per gallon, that's roughly 8 extra miles. On a 1.5 mile superspeedway, that's 5 additional laps before a pit stop was necessary. 5 laps. In a sport where track position is measured in fractions of seconds, 5 laps is an eternity. It's the difference between leading and chasing, between winning and being a footnote. But Smokey wasn't finished. Not even close. Because here's what most people don't realize about the fuel line trick. It wasn't the end of his thinking. It was the beginning. The fuel line was the foundation. The first layer of a system so elegantly constructed that even when inspectors found individual pieces of it, they couldn't see the whole picture. It's like being shown one piece of a jigsaw puzzle and being asked to describe the image. Without context, the piece is meaningless. The second layer was thermodynamics. And this is where Smokey's aerospace mechanic background really started showing itself. Gasoline, like most liquids, contracts when it's cold and expands when it's warm. This isn't exotic physics. This is basic chemistry. But nobody in NASCAR was thinking about it as a competitive tool, because nobody in NASCAR was thinking the way Smokey thought. Here's the thing about gasoline density. A gallon of fuel at 35 degrees Fahrenheit is measurably denser than a gallon at 80 degrees. When that cold fuel warms up inside the tank during a race, it expands. It doesn't create extra fuel from nothing, but it does mean the energy content per measured volume is higher at lower temperatures. Fill a 22-gallon tank with fuel cooled to near freezing, and as it warms to ambient temperature during the race, you effectively access a slight but meaningful volume advantage. Smokey calculated that supercooled fuel gave him roughly an additional 3/4 of a gallon in effective volume over a standard fill. Combined with the 11-foot fuel line holding nearly 2 gallons, his cars were now carrying the equivalent of close to 25 gallons, while every inspector on the property had signed off on 22. The math was invisible if you only looked at individual components. The system only revealed itself if you understood how all the pieces interacted simultaneously. Now, Junior Johnson, who was himself absolutely no stranger to creative mechanical interpretation, later admitted he spent months trying to figure out how Smokey's cars ran so impossibly long between pit stops. Johnson's exact words were something close to, "We tore our own cars apart looking for hidden tanks. We never thought to measure the fuel line." And that quote is actually more illuminating than it first appears, because it reveals the fundamental cognitive trap that Smokey had laid for his competitors. Everyone was searching for something hidden. A concealed compartment, a fake fuel cell, a secret tank buried somewhere in the chassis. because that's the obvious way to carry extra fuel. You put more fuel somewhere the inspectors aren't looking. Smokey understood that approach would always eventually fail, because inspectors who know they're being fooled will eventually find a hidden tank if they look hard enough and long enough. So Smokey didn't hide anything. Everything was visible. The fuel line was right there. The oversized tubing was accessible. The cooled fuel was in the tank. Nothing was concealed. It was just interpreted differently than anyone expected. This is a genuinely sophisticated piece of psychological engineering layered on top of the mechanical engineering. Smokey wasn't just fooling inspectors with hidden components. He was exploiting the assumption that extra fuel had to be hidden. By making everything visible but misunderstood, he created a misdirection so complete that inspectors didn't even know they'd been fooled. Look, the beauty of this approach becomes even clearer when you understand how NASCAR officials responded. They descended on Smokey's cars after performances that defied their calculations. At one point, after a particularly dominant showing at Daytona, they literally disassembled the car, cut open body panels, brought in measuring equipment, X-rayed sections of the frame. They found the oversized fuel line eventually, and they stood there looking at it, trying to figure out if it was illegal. And this is where it gets really interesting, because it wasn't illegal. There was nothing in the rulebook that said a fuel line couldn't be 2 inches in diameter. There was nothing specifying it had to be less than 11 feet long. There was nothing prohibiting it from being routed through every corner of the car. Bill France Sr., NASCAR's founder and president, knew he was being outplayed. He also knew he couldn't penalize someone for violating a rule that didn't exist in writing. That's not how sporting governance works, at least not sporting governance with any credibility. France was also caught in a second bind that doesn't get discussed enough. Smokey Yunick was box office. He was one of the most compelling personalities in the garage area. Fans loved the outlaw mechanic who outwitted the establishment. Sponsors liked his cars because his cars won, or at least ran extraordinarily well. The press followed him because he was always good for a quote, always doing something unexpected, always making the story more interesting. Penalizing him without cause wouldn't just be legally indefensible, it would be a public relations disaster. So NASCAR did what governing bodies always do when they can't catch the rule bender in the moment. They changed the rules. In 1968, the rulebook was updated to specify a maximum fuel line diameter of 1.5 inches. Smokey responded immediately. He built a fuel line with an internal diameter of exactly 1.5 inches, but with walls so thick the external diameter approached 2 inches. When officials raised their eyebrows, Smokey pulled out the updated rulebook and pointed to the relevant line. Maximum internal diameter, 1.5 inches. This line has an internal diameter of 1.5 inches. Show me the violation. They changed the rule again. Maximum outside diameter 5/8 of an inch, effectively standardizing fuel lines at something approaching normal proportions. At this point, most people would pivot. Find a different loophole. Move on to other areas of the car. Smokey pivoted too. But he pivoted in the most Smokey way imaginable. He went deeper into thermodynamics. The cooling system he developed for his fuel in the next phase was genuinely sophisticated engineering. Using dry ice integrated into the fuel storage system, he was cooling gasoline to approximately 20 degrees below 0 Fahrenheit before races. At that temperature, gasoline takes on a noticeably different viscosity. It flows more slowly, almost syrup-like, but its energy density per unit volume increases measurably. The fuel would warm progressively during the race as the car's heat soaked through the chassis and fuel system components, expanding and providing volume exactly when the engine needed it most, typically in the final stages of a fuel run when the tank was running low, and every additional fraction of a gallon mattered for strategy decisions. NASCAR's response was to mandate fuel temperature checks during pre-race inspection, which meant inspectors would measure the temperature of fuel in the tank before the car took the grid. ensuring nothing suspiciously cold was going in. Smokey's response to this was a secondary circulation system that routed room temperature fuel through the tank during inspection, displaying a normal temperature reading at the point of measurement. While the bulk of the cooled fuel remained in sections of the system, the temperature probe wasn't reaching. When officials tightened inspection protocols further, requiring that whatever fuel was in the car during inspection had to be the fuel it raced on, Smokey developed quick disconnect fuel system fittings that his crew could swap in under 30 seconds between inspection and the car moving to the grid. The officials would sign off, the car would roll away, and by the time it reached its starting position, the fuel system configuration had changed. The escalation was relentless and genuinely fascinating to study from a systems perspective. Every rule NASCAR wrote was specific, targeting one exact innovation. And every specific rule created new adjacent spaces that Smokey could explore. Tighten the diameter rule, and you push innovation toward temperature manipulation. Regulate temperature, and you push innovation towards system configuration. Regulate system configuration, and you push innovation toward timing and process, rather than hardware. Smokey wasn't just finding loopholes. He was demonstrating, repeatedly and empirically, that a rulebook written reactively in response to specific innovations will always lag behind creative engineering. Because the rulebook describes what already happened, creative engineering describes what hasn't been thought of yet. This is where his approach diverges most sharply from ordinary cheating, and it's worth being clear about this distinction because it matters for understanding his legacy. An ordinary cheat tries to do something the rules prohibit and hopes not to get caught. The risk is detection. The innovation is minimal. The cheat is trying to secretly cross a line that everyone agrees exists. Smokey was doing something categorically different. He was operating in space that the line hadn't yet been drawn through. The rules didn't prohibit what he was doing because nobody had imagined someone would do it. That's not cheating. That's a form of adversarial creativity that has genuine intellectual merit, even if it frustrated every competitor and official who encountered it. And the proof of that distinction is in how NASCAR responded. You don't rewrite your rulebook 17 times in response to cheating. You eject the cheater. You rewrite your rulebook 17 times in response to someone who is technically, infuriatingly, demonstrably correct. The fuel return line innovation is probably the least discussed piece of Smokey's system, which is genuinely surprising because it might be the most elegant engineering of everything he developed during this period. And understanding it requires thinking about fluid dynamics, vehicle physics, and oval track geometry simultaneously, which is exactly the kind of multi-system thinking that separated Smokey from every other mechanic in the garage. Here's the setup. NASCAR rules in the late 1960s said nothing specific about fuel return lines. A fuel return line is the line that carries unused fuel back from the carburetor to the tank. In a standard racing fuel system, the fuel pump moves more fuel than the engine actually consumes at any given moment. The excess returns to the tank through the return line. Standard practice was a small diameter return line running a direct path back to the tank. Functional, efficient, completely uninteresting. Smokey looked at that return line and saw a reservoir. He built his return line system with a section of significantly enlarged tubing, essentially a secondary chamber holding approximately 1 additional gallon of fuel, positioned at a very specific location relative to the car's center of gravity and the direction of cornering forces on an oval track. Here's where the physics gets beautiful. Every oval track in NASCAR turns left. When a car turns left, centrifugal force pushes everything to the right. Fuel in a tank sloshes to the right side under cornering loads. This is why racing fuel cells have internal baffles, to prevent fuel starvation as the tank empties and fuel moves away from the pickup point. Smokey understood this force not as a problem to manage, but as a mechanism to exploit. He positioned his return line reservoir on the right side of the car, high enough that gravity and cornering forces working together would gradually drain it into the main fuel system throughout the race. Every left-hand corner, of which there are thousands in a 500-mile NASCAR race, applied a small but consistent force pushing fuel from his hidden reservoir toward the main tank pickup. The system was entirely passive. No pumps, no valves, no moving parts that could be identified during inspection. Just geometry and physics doing exactly what physics always does, completely invisibly, lap after lap after lap. The inspector looking at this car would see a return line. They'd see it was somewhat larger than typical in one section. They might even note it and move on, because the rulebook said nothing about return line dimensions. What they wouldn't see, what they couldn't see without understanding the entire system as a unified whole, was that this return line was also a fuel storage and delivery system that exploited the very nature of oval racing to feed itself. Now, you might be thinking, okay, 1 gallon extra from the return line, 2 gallons from the fuel line, a fraction more from temperature manipulation. This is starting to sound like a lot of incremental gains adding up. And you're absolutely right, which is precisely the point. Each individual element, examined in isolation, looks modest. The oversized fuel line? A minor capacity gain. The cooled fuel? A small density advantage. The return line reservoir? A passive gallon of extra range. But Smokey never thought in isolation. He thought in systems. Combined, these innovations gave his cars a genuine and consistent advantage of between 2.5 and 3 gallons of effective fuel capacity over a competitor running an identical engine in a car built to the letter of what everyone else understood the rules to require. At 4 miles per gallon race pace, that's 10 to 12 additional miles per fuel load. At Charlotte Motor Speedway, running 1.5 miles per lap, that's 7 to 8 extra laps. 7 to 8 laps is not a minor strategic edge. 7 to 8 laps is a completely different pit stop strategy. It's the difference between pitting when your competitors pit and pitting when you choose to, on your terms, at the moment that best serves your race. The 1968 Daytona 500 is probably the clearest illustration of what this advantage looked like in practice. Gordon Johncock, driving a Smokey-built car, was running laps with a consistency that baffled the field. Competitors were making calculated pit stop decisions based on standard fuel consumption math. The same math every crew chief in the garage used, built on years of empirical data about how much fuel a stock car consumed per lap at Daytona speeds. Johncock's car was simply not consuming fuel at the rate that math predicted. He was running 62 laps on a tank. Competitors were managing 55. That 7-lap gap was compounding into strategic advantages that played out over the entire race distance. Crew chiefs on other teams were genuinely confused in a way that went beyond competitive frustration. Their fuel consumption models were built on solid data. They'd measured their own cars hundreds of times. They knew what a stock car should consume. When another car's consumption didn't match the model, the natural assumption was a hidden tank, because that was the only explanation that fit the existing mental framework. Nobody's mental framework included an 11-foot fuel line and a thermodynamically cooled fuel system and a passive return line reservoir, all working together as a unified system, because nobody had ever built anything like that before. Junior Johnson spent months, and reportedly considerable money, trying to reverse engineer what Smokey was doing. The story goes that Johnson's team eventually identified the oversized fuel line but still couldn't account for the full advantage, because they found one piece of the puzzle and assumed they'd found the answer. Finding the fuel line without understanding the temperature system and the return line reservoir was like finding one ingredient in a recipe and assuming you knew the whole dish. Ray Fox Racing reportedly invested somewhere in the range of $50,000 in 1968, which translates to approximately $400,000 in today's money, specifically trying to understand and replicate Smokey's fuel system advantages. When they finally developed a partial understanding and implemented some of his techniques, their cars immediately improved by roughly 2 positions in average race finish. 2 positions doesn't sound dramatic until you understand what it means financially and competitively in a sport where the prize money curve drops steeply from the front. The psychological dimension of all this deserves serious attention because it was as deliberately engineered as the mechanical systems. Smokey understood that inspectors, like all humans, have limited attention and cognitive bandwidth. They can only focus on so many things simultaneously. So he gave them things to focus on, deliberately, strategically, as a form of misdirection that would make a stage magician envious. He would show up to inspection with cars that had obvious, visible anomalies. Not illegal anomalies, but unusual ones. Routing choices that looked strange. Components that appeared oversized. Fabrication that differed from standard practice in ways that were immediately visible but ultimately unimportant. While inspectors spent their time and attention examining and ultimately clearing these visible oddities, the actual innovations, the ones that mattered competitively, sat quietly in plain sight, unexamined because the inspection team's bandwidth was already consumed. At one particularly well-documented event, Smokey's car arrived with visible nitrous oxide lines running to the intake manifold. Bold, obvious, impossible to miss. Officials spent hours confirming that the nitrous system was entirely non-functional, which it was. It had never been intended to function. It was theater. While that inspection consumed the afternoon, nobody looked carefully at the fuel cell mounting position, which Smokey had relocated in a way that added approximately 3 gallons of usable capacity by changing the geometry of the fuel pickup relative to the cell's actual volume. This level of strategic misdirection requires not just mechanical ingenuity, but genuine psychological sophistication. You have to understand how inspectors think, what they're trained to look for, how their attention moves through a car during inspection, what triggers concern and what gets waved past. Smokey had been in these inspection bays hundreds of times. He understood the process from the inside, and he used that understanding the way a chess player uses knowledge of their opponent's tendencies, not just to make good moves, but to make moves that lead his opponent toward bad ones. The Firebird he built for Trans Am racing in 1968 represented perhaps the most audacious single piece of engineering from this entire period. The rulebook for that series required that the car retain its stock floor pan. A stock floor pan is a specific structural component, the pressed steel floor of the production car, and the rule was designed to prevent teams from replacing it with a custom fabricated floor that might hide fuel capacity or other advantages. Smokey read that rule very carefully. It said the car must retain the stock floor pan. It said nothing about the condition of the stock floor pan. So Smokey acid-etched the original floor until it was, and this is not an exaggeration, approximately as thick as heavy aluminum foil. Structurally, essentially nothing. But it was there. You could see it if you looked. It was, technically, the stock floor pan retained in the car exactly as the rules required. Beneath this tissue-thin remnant of the original floor, Smokey installed a new structural floor that also functioned as a 5-gallon fuel cell. The class fuel limit was 22 gallons. His car carried 27. The stock floor was present and visible. The rule was satisfied in every literal sense. The intent of the rule was comprehensively, brilliantly, almost artistically violated. When SCCA officials eventually understood what they were looking at and moved to disqualify the car, Smokey's response became one of the most quoted moments in motorsport history. As officials removed the fuel system components for evidence, Smokey picked up his 11-foot fuel line, now disconnected at both ends from anything, and began walking it to his truck. An official stopped him and said they needed to inspect it. Smokey's response was delivered with the calm certainty of a man who has already thought 10 moves ahead. The rulebook says the fuel line runs from the tank to the engine. This isn't connected to the tank. It isn't connected to the engine. By definition, it isn't a fuel line, it's a tube. And he walked to his truck. The official stood there holding a clipboard, looking at the space where Smokey had just been standing, and had absolutely nothing to say. Because Smokey was right. Not morally right, perhaps. Not right in the sense of honoring the spirit of what everyone in that garage understood the rules to mean, but right in the only way that matters in a technical dispute, which is literally, documentably, provably right. The rules said what it said. The tube wasn't connected to anything. The argument was airtight. This moment captures something essential about Smokey Yunick that goes beyond motorsport and touches on something genuinely interesting about how humans construct rules and how creative minds interact with those constructions. Every rule is written in language. Language is inherently imprecise. Words mean different things in different contexts. The gap between what a rule is intended to prevent and what it actually prevents in its written form is always wider than the people who wrote it intended. Smokey didn't create that gap. He just had the engineering genius and the legal precision of mind to find it and exploit it before anyone else thought to look. Now, here's what most people don't realize about the broader impact of everything Smokey was doing during this period. The conversation almost always stays at the level of NASCAR, of stock car racing, of one clever mechanic outsmarting one governing body in one American motorsport series during a specific decade. That framing dramatically undersells the actual significance of what he developed. The fuel cooling and density manipulation techniques Smokey pioneered in NASCAR were studied by engineers well outside of motorsport. NASA, specifically engineers working on rocket propellant management systems in the late 1960s and early 1970s, looked carefully at Smokey's approach to fuel temperature control and the relationship between stored fuel temperature, density, and effective volume at point of consumption. Rocket fuel management has its own version of this problem. You need to know exactly how much propellant you have, exactly what its energy density is, and exactly how it will behave as temperature changes during the mission. Smokey was solving a simplified version of the same problem on an oval track in Florida, and the solutions, while obviously different in scale and complexity, shared underlying principles worth examining. The military application is equally interesting. Extended range vehicle operations, specifically the challenge of maximizing fuel carried in a given volume while accounting for temperature variation in extreme environments, drew on work that traced conceptual lineage back to exactly the kind of distributed fuel system thinking Smokey had been doing. Hidden reservoir systems, passive feed mechanisms, the exploitation of vehicle dynamics to move fuel without dedicated pumping systems. These ideas show up in military vehicle design documentation from the 1970s onward in ways that suggest engineers were thinking along parallel tracks, even if they weren't directly citing a NASCAR mechanic from Daytona Beach. The motorsport legacy is more direct and more traceable. Modern fuel cell design across essentially every form of professional motorsport incorporates internal baffle systems that manage fuel movement under cornering and braking loads. The sophistication of those baffle systems, their geometry, their material construction, the way they're integrated with the pickup and return line architecture, owes a genuine debt to the work Smokey was doing in the 1960s. He was building internal fuel cell architecture for competitive advantage while everyone else was building it simply for function. The distinction matters because optimizing for advantage requires thinking about the system under dynamic racing conditions, not just static bench conditions, and that deeper level of analysis produced insights that pure functional engineering would have taken much longer to arrive at. Formula One's relationship with fuel system innovation follows a slightly different trajectory, but arrives at similar conclusions about Smokey's influence on how the sport thinks about regulatory space. The FIA today employs what amounts to a dedicated team of engineers whose specific function is anticipating creative rule interpretation before teams can exploit it. This is a direct institutional response to the repeated experience of technical regulations being outpaced by engineering creativity. The job literally exists because governing bodies learned, through painful, repeated experience across multiple decades and multiple series, that reactive rule writing always loses to proactive, creative engineering. Smokey didn't create that lesson alone, but he delivered it more comprehensively and more repeatedly than anyone else in motorsport history. The financial scale of the competitive advantage he created is worth examining in concrete terms, because it contextualizes just how significant the strategic impact of extra fuel range actually was. In 1968 NASCAR racing, prize money for a top 5 finish at a major superspeedway event was roughly 3 to 5 times the prize money for a 10th place finish. The difference between running a 7-lap longer fuel stint and running a standard stint wasn't just track position on that particular lap. It was the compound effect of track position on pit cycle timing, on tire management, on the ability to respond to caution periods, on the psychological pressure applied to competitors who knew your car was doing something their math said was impossible. Dale Inman, one of the most respected crew chiefs in NASCAR history, and the man behind Richard Petty's championship campaigns, said something in a later interview that cuts directly to this point. He said that competing against Smokey's cars wasn't just technically frustrating. It was psychologically destabilizing. When your competitor's car consistently defies your mathematical models of how racing should work, you start questioning your own data. You start wondering if your fuel consumption numbers are wrong, if your fuel flow calculations have an error, if your engineers miss something fundamental. That self-doubt is itself a competitive disadvantage, entirely separate from the actual mechanical advantage Smokey's cars possessed. Look, this is actually a well-documented phenomenon in competitive psychology. When an opponent consistently performs beyond what your mental model predicts is possible, the natural response isn't immediately to assume they've found a loophole. The natural response is to assume your model is wrong. Teams spent months questioning their own engineering before they started seriously investigating whether Smokey had found something in the rules rather than something in the physics. That delay, that period of self-doubt and internal recalibration, was itself a gift Smokey hadn't explicitly engineered but absolutely benefited from. The escalation pattern between Smokey and NASCAR's rule writers over the period from roughly 1965 to 1970 is genuinely fascinating when you chart it systematically. NASCAR writes a rule targeting a specific innovation. Smokey finds the adjacent space the new rule opened by closing the previous one. NASCAR writes another rule targeting the new innovation. Smokey moves to the next adjacent space. The rule book grows not in response to cheating, but in response to creativity. And each new rule is slightly more sophisticated than the previous one, because both sides are learning. This is actually a well-understood dynamic in regulatory economics and game theory. It's called an adversarial spiral, and it appears everywhere from tax law to securities regulation to pharmaceutical approval processes. A regulation written to prevent a specific behavior creates incentives to find the nearest compliant behavior that achieves the same economic outcome. The regulator writes a new rule targeting the compliant behavior. The regulated party finds the next adjacent space. The rulebook grows. The compliance industry grows. The system becomes more complex without necessarily becoming more effective. What makes Smokey's case historically interesting is that he was running this dynamic in a domain, motorsport technical regulation, where it hadn't really been seen before at this level of sophistication. He was essentially introducing adversarial regulatory dynamics to a sport that had been operating on a gentleman's agreement model, where the spirit of the rules was assumed to be self-enforcing because everyone agreed on what the spirit was. Smokey didn't agree. Or more precisely, Smokey agreed on the spirit and simply maintained that the spirit was subordinate to the letter when it came to technical inspection. The 1969 and 1970 NASCAR seasons represented the peak of the escalation. NASCAR had by this point rewritten the fuel system regulations multiple times, each iteration more specific and more exhaustive than the previous one. They'd standardized fuel cell dimensions with detailed specifications. They'd specified acceptable fuel line diameters and maximum lengths. They'd introduced temperature monitoring during inspection. They'd required that fuel system configurations be locked and sealed before the car moved from inspection to the grid. Smokey's response to this increasingly comprehensive regulatory environment was to shift his innovation focus. When the fuel system became too tightly regulated to exploit easily, he moved to chassis geometry, to aerodynamic interpretation, to engine breathing. The specific technical domain changed, but the methodology remained identical. Read the rule. Find what it specifies. Find what it doesn't specify. Work in the unspecified space with the most sophisticated engineering you can bring to bear. Force the rule writers to catch up. This is where a broader competitive truth about Smokey's career becomes visible. He was never specifically a fuel system innovator, or a chassis innovator, or an aerodynamics innovator. He was a systems thinker who happened to be applying his thinking to racing cars within a regulatory environment. The fuel system was just the most extended and most documented example of his methodology, because the fuel system happened to offer the richest regulatory gaps during the period when his reputation was being established. But the methodology was consistent across every aspect of every car he built. Junior Johnson, reflecting on this period decades later, made a comment that deserves to be quoted at length because it captures the competitive dynamics so precisely. Johnson said something to the effect that racing against Smokey was an education that no school could have provided. You learn to think about rules differently. You learn to think about cars differently. You learn that the car you built wasn't just a mechanical device. It was an argument about what the rules permitted, expressed in steel and aluminum and rubber. And Smokey's arguments were always better than everyone else's, because he'd thought about them longer and harder, and from more angles than anyone else was willing to. That framing, the car as an argument about regulatory interpretation, is actually quite profound, and explains why Smokey's influence extends so far beyond the specific innovations he developed. The cars he built weren't just faster, they were more carefully reasoned. They were constructed from a foundation of deep regulatory analysis and then engineered to express that analysis in physical form. Every component was where it was not just because it worked, but because the rules permitted it to be there in a way that generated competitive advantage. NASCAR Hall of Fame inspector and longtime technical director Gary Nelson, who built his own legendary career finding hidden fuel and finding other creative interpretations of technical regulations, has said publicly that studying Smokey's approach was formative for his own understanding of how creative engineering and regulatory interpretation interact. Nelson came at the problem from the other side, trying to find what teams were hiding rather than hiding it himself, but the analytical framework required is remarkably similar. You have to think like the engineer who built the car to find what they built into it. And thinking like Smokey required a level of systematic creativity that Nelson has described as unlike anything else he encountered in decades of technical inspection. The safety dimension of Smokey's fuel system work is perhaps the most counterintuitive part of his legacy, because the instinctive assumption is that carrying more fuel in unusual configurations must be more dangerous. The reality is considerably more nuanced. Smokey's distributed fuel system design, precisely because it spread fuel through multiple interconnected volumes, rather than concentrating it in a single large cell, actually reduced the risk of catastrophic fuel release in certain crash scenarios. A single large fuel cell struck directly can release its entire contents in one event. A distributed system with multiple smaller volumes connected by lines that separate under impact loads releases fuel in smaller quantities from each point of failure. The internal baffling Smokey developed to manage fuel movement within his creative system configurations also produced handling benefits that were genuinely valuable, independent of any capacity advantage. Fuel slosh. The movement of liquid fuel within a partially filled tank under braking, acceleration, and cornering loads is a real and significant handling variable in racing. As fuel burns off during a stint, the amount of slosh increases because there's more empty space for the remaining fuel to move through. This changing dynamic means the car's handling characteristics shift throughout a fuel run in ways that drivers have to constantly manage and compensate for. Smokey's baffle systems, designed primarily to hide capacity and manage fuel pickup reliability, happened to also dramatically reduce fuel slosh compared to standard fuel cell designs of the era. His drivers were therefore experiencing more consistent handling characteristics across a longer portion of their fuel run than competitors whose cars were sloshing more aggressively as fuel levels dropped. Dale Inman noted this specifically when reflecting on races where Smokey's cars seemed to maintain their pace better in the late stages of long fuel stints than physics and tire wear alone could explain. Part of the answer was strategic fuel range. Part of it was that the car was simply handling more consistently because the fuel wasn't moving around as much. This is the kind of compounding advantage that makes Smokey's work so difficult to fully account for, even in retrospect. Each innovation produced primary benefits, the ones he designed for, and secondary benefits, the ones that emerged from the interaction of his innovations with the physical realities of racing. The baffle system was designed to hide capacity and prevent fuel starvation. It also improved handling consistency. The distributed fuel system was designed to carry more fuel past inspection. It also improved crash safety characteristics. The cooled fuel system was designed to increase effective energy density. It also reduced fuel volatility during the early laps of a race when the car was at its heaviest and crash risk was statistically highest. None of these secondary benefits were accidental in the sense of being unforeseeable. Smokey was smart enough to know they existed, but they weren't the primary engineering objective either. They were the natural product of building systems that were comprehensively thought through rather than optimized for a single variable. This is the difference between engineering and clever tinkering. Clever tinkering optimizes one thing and ignores everything else. Engineering understands that every component exists in relationship with every other component, and that a change to one part of a system ripples through all connected parts in ways that can be predicted, managed, and exploited. Here's the thing about Smokey's relationship with safety that most historical accounts completely miss. He was genuinely concerned with driver safety in ways that went beyond competitive necessity. His autobiography contains extended passages about the responsibility he felt toward the drivers who trusted his cars. He pushed for better fuel cell construction, better rollover protection, better fire suppression systems, not just because safer cars won more races by finishing rather than crashing out, but because he believed the sport had a genuine obligation to the men who drove in it. The fuel system work he did that happened to improve crash safety characteristics wasn't incidental to who he was. It was consistent with a value system that ran alongside the competitive obsession. This matters for understanding his legacy, because it complicates the simple narrative of Smokey as pure outlaw. He was an outlaw with a moral framework. He bent rules he considered arbitrary and poorly constructed. He respected rules he considered genuinely important for the sport's integrity and its participants' safety. The distinction he drew between those two categories wasn't always one that NASCAR's officials shared, but it was internally consistent in a way that pure rule-bending for its own sake never is. By 1970, the regulatory environment had tightened to the point where the specific fuel system innovations Smokey had been running for half a decade were largely closed off. NASCAR's rulebook had grown from approximately 20 pages in 1960 to something approaching 60 pages by the end of the decade, with the fuel system section alone running to several pages of specific, detailed requirements that would have been unrecognizable to the officials who'd been enforcing a half-page of general guidelines in 1965. Every page of that additional regulatory text represented a specific response to something Smokey had done, or something another team had done while following the trail Smokey blazed. The modern NASCAR rulebook runs to over 200 pages. The fuel system section alone occupies 14 pages of detailed specifications covering fuel cell construction, approved materials, maximum dimensions, mandatory safety features, fuel line specifications including both internal and external diameter and maximum allowable length, fuel temperature requirements, inspection protocols, sealing requirements, and approved supplier lists. In 1967, the same subject occupied roughly half a page. Those additional 13.5 pages of fuel system regulation are, in a very real and traceable sense, the Smokey Yunick Memorial Amendments, written in response to what one mechanic from Daytona Beach demonstrated was possible when you applied genuine engineering intelligence to regulatory analysis. The current specification fuel cell used in NASCAR Cup Series racing is a sealed unit manufactured by a single approved supplier, constructed to precise dimensional specifications, fitted with tamper-proof seals that are verified at multiple points during the inspection process, and monitored electronically during races through fuel flow sensors that track every fraction of a gallon entering and leaving the system in real time. The romance of the fuel line running 11 feet through the chassis is entirely gone. The precision of modern digital monitoring has replaced the cat-and-mouse game of physical inspection. It's more controlled, it's more equitable, and it's considerably less interesting. There's a genuine loss there worth acknowledging. Not a loss of cheating, because as we've established, Smokey wasn't cheating in any meaningful sense. A loss of the creative tension between engineering ingenuity and regulatory construction that produced some of the most intellectually interesting moments in motorsport history. The modern regulatory environment is designed precisely to prevent that tension from emerging, which makes the racing more controlled and probably more fair in a narrow technical sense, but also removes the possibility of the kind of genius that Smokey represented. This is where it gets really interesting when you consider the broader sporting philosophy question his career raises. Is a sport better when it constrains creative engineering interpretation to create a level technical playing field? Or is it better when it allows creative interpretation to flourish, accepting that the playing field will be uneven in ways that reward engineering intelligence alongside driving skill and team execution? Different people answer that question differently, and the answer reveals something about what you think sport is actually for. If sport is primarily a test of a specific set of defined skills, driving ability, pit stop execution, race strategy within a defined set of parameters, then tight technical regulation makes sense. You want the variable being tested to be isolated as cleanly as possible from confounding variables like engineering creativity. If sport is primarily a test of comprehensive competitive excellence, including the intelligence to find advantages within the rules and the engineering capability to execute on those advantages, then tighter regulation reduces the scope of what's being tested in ways that might actually make the competition less meaningful, not more. Smokey believed strongly in the second view. He thought that a race car was as much an engineering argument as a mechanical device, and that the team which made the best engineering argument within the rules deserved to win. He had no patience for the idea that everyone should run identical cars, or cars constrained so tightly that engineering creativity was effectively eliminated from the competitive equation. He saw that approach as fundamentally misunderstanding what made motorsport worth watching and worth caring about. The Formula One approach to this question has oscillated dramatically over the decades. Early Formula One was extraordinarily open technically, producing cars of wildly different configurations as teams explored the entire solution space of what a racing car could be. Gradually, restrictions accumulated, closing off solution spaces one by one in response to either safety concerns or competitive dominance by specific technical approaches. Today's Formula One operates under what the FIA calls a technical regulation framework, but which is in practice an enormously detailed specification document that constrains virtually every meaningful design parameter while leaving enough freedom in specific areas to allow genuine engineering differentiation. The areas where differentiation is still permitted: aerodynamic development within defined bodywork zones, power unit thermal efficiency within specified architectural constraints, suspension geometry within defined kinematic envelopes, are areas where teams spend hundreds of millions of dollars annually seeking advantages measured in fractions of a second per lap. The scale is incomprehensibly larger than Smokey's garage in Daytona Beach. The methodology is remarkably similar. Read the regulation. Find what it specifies. Find what it doesn't specify. Work in the unspecified space with the best engineering you can bring to bear. Red Bull Racing's flexi-wing controversies of the early 2020s, where their rear wing was found to deform under load in ways that reduced drag on straights while complying with static load deflection tests specified in the regulations, would have made Smokey smile. The regulation specified how much the wing could deflect under a static load applied at specific points during a stationary test. It said nothing about aerodynamic loads in motion at racing speeds. The wing passed every test. It did something the regulations hadn't anticipated. Sound familiar? Mercedes' dual-axis steering system from 2020, which allowed drivers to adjust front wheel toe angle by pushing and pulling the steering wheel, exploited a regulatory gap in ways that forced an immediate rule clarification for the following season. Legal in the year it ran, gone the next year. Smokey would have recognized the pattern immediately. It's the same pattern he ran for 5 years in NASCAR. Find the gap, exploit it comprehensively, force the rule writers to close it, move to the next gap. The language has changed. The budgets are unrecognizable. The technical complexity is orders of magnitude greater, but the fundamental dynamic, creative engineering intelligence and adversarial dialogue with reactive regulatory construction is identical to what Smokey was doing with an 11-foot fuel line in 1967. He didn't invent this dynamic. Human competitive ingenuity has always found the edges of whatever constraints it operates within. But he demonstrated it so clearly, so repeatedly, and so publicly that he effectively taught a generation of engineers and officials what adversarial regulatory creativity looked like at its highest level. Smokey Yunick passed away in May 2001 at the age of 77. The tributes from across motorsport were extraordinary in their consistency. Everyone, competitors who'd hated racing against him, officials who'd spent years trying to catch him, journalists who'd covered him for decades, said essentially the same thing in different words. He made everyone around him better by forcing them to think harder than they wanted to. He elevated the standard of engineering thinking in American motorsport by decades. He changed not just what race cars look like, but how the people who built them thought about the relationship between rules and innovation. The 11-foot fuel line is illegal in every form of professional motorsport on Earth today. The cooled fuel system is prohibited. The passive return line reservoir is prohibited. The acid-etched floor pan is prohibited. Every specific innovation Smokey developed has been specifically closed off by regulations written explicitly in response to it. And yet his influence is everywhere in modern motorsport, embedded not in any specific technical solution but in the methodology, the relentless, systematic, creative application of engineering intelligence to the space between what the rules say and what they mean. There's a saying that's been attributed to Smokey in various forms over the years, though like most good quotes its exact origin is somewhat uncertain. The version most often repeated goes something like this: the rulebook tells you what you can't do. Everything else is still available. That philosophy, stated so simply it almost sounds trivial, is actually a complete and sophisticated theory of competitive engineering. It reframes the rulebook from a constraint to a map. It reframes compliance from a ceiling to a floor. It reframes the competitive question from how do we follow the rules to how do we win within them, which turns out to be a completely different question with a much richer set of possible answers. Every team principal in Formula One knows this philosophy, whether or not they know it came from a stock car mechanic in Florida. Every technical director in endurance racing operates by it. Every regulations analyst in any professional motorsports series is paid specifically to apply it. The institutionalization of what was once one man's individual genius is perhaps the truest measure of how profoundly Smokey Yunick changed the sport. He thought a certain way about rules and engineering that was unique to him in his time. Now entire departments think that way as standard professional practice. Racing needed Smokey Yunick in exactly the way that any system occasionally needs someone who sees it completely differently from everyone else operating within it. Not to break it, not to corrupt it, but to reveal its assumptions, expose its gaps, and force it to become more sophisticated than it would have been if everyone had simply agreed on what the rules meant without anyone ever testing that agreement against the actual text. The next time you watch a race and a team finds a creative interpretation of the technical regulations, the next time an innovation forces a mid-season rule clarification, the next time someone in a garage somewhere asks the question, does the rule book actually say that, you're watching Smokey's ghost still working the room, still reading more carefully than everyone else, still finding the space between what's written and what's meant, still making everyone around him think harder than they thought they needed to. That's the real 11-foot fuel line, not the steel tube coiled through a 1967 stock car. The idea that the distance between a rule and its limits is always longer than anyone first measures, and that genius lives in every inch of that unmeasured space.